Hello and welcome to another tutorial. My name is Robin and I want to show you a good example of grabbing data from the internet that's a little bit unformatted or that requires a little bit more work to get into a usable format. And quite often this data is in tabular format, and so you can work with a spreadsheet in order to turn it into something usable. So that's basically what I want to look at today. And I'm on this NASA website for the Parker Solar Probe, which is really quite interesting and slick here. The way they've done this craft, which is about the size of a car, apparently, was launched to get closer to the sun than any other satellite has before. So they show you here the orbits. Essentially, it's got this highly eccentric orbit so that on one swing it gets really close to the sun. I think it's done it 3 times now, if I'm not mistaken, and it says in 35 days it will actually have another solar encounter. But the interesting thing about this is they produce this really nice website for the general public and those that are just interested in following astronomy. But there's also if you drill down, well, it says right here, the data is now available to the public from the 3rd orbit. And if you drill down to the Goddard Space Flight Center, I actually found this page, which took some finding, I have to say, but I found this page that has data from all sorts of different satellites through history. And you can look at it in different ways. So if I look at the Parker Solar Probe here on this line, graphical browse and listing. I'll just click on that. Those are actually buttons, believe it or not. And so you get this kind of page here. You can plot the data, list the data, or create a file. How about I create a file based on hourly averaged data? And I'm going to grab that for a certain time period. Now, from their other press release, I know the time period I want because it's the time period of the 3rd orbit. And I've put that already here in my header. So it's from June 18th to November 15th of 2019. So I've already got those numbers sorted out here. So just to save some time, I'll just copy and paste into here. And then there's all these different variables you can get. Now, of course, the more you know about astronomy and physics, the better. I don't know what all of these mean myself, but I think if I get the proton density and the proton temperature, those two would be kind of interesting. The density should increase and the temperature should increase as this craft gets closer to the sun. And yeah, I don't really know what to say about the rest of this, so I'll just leave it and submit my data request. So instantly it generates this data, and there are 2 files. So I'll just download both of those. The first says is an ASCII data file, and the second is the format description, which is very short. It's just to tell us what the data headers mean. So I'll download both of these. Let me close this up for now, and I'll put it in my folder. So here is my folder for this project that I've already started with some skeletal files. Here's the data, and here we have it. So if we take a look at what's in these files that we just got. So first of all, the data itself looks like this, and there's quite a few lines here because we're grabbing it for a good amount of 2019. A lot of this looks kind of crazy, like a lot of 9s, like it's not really good data. We'll have to check that out in a moment. Here's the data format. It just says items and the format. So the year is an integer I4, an integer of length 4. The day of the year. So you've got year, you've got the day of the year, which is a number. So the 169th day of the year, and then hours 0 through 23, and then for the 170th day of the year, it's hours 0 through 23. So it's a number for every hour. But I do notice that a lot of these values, like these values are supposed to be IFMB scalar. I don't know what that is. I didn't even request that. I don't know what but the proton fit density in newtons per centimeter cube. Okay, so that is a measure of density. And then the proton fit temperature in degrees Kelvin. Okay, density and temperature I can understand. I don't know what the other one is, but they're all weird values. So if I go down through here, I'm going to assume that these are zeros. I'm going to assume that when this craft registers 0, it puts in this giant number instead. Whoops. Here we go. We're starting to see something. So some useful data is coming in, I guess. Ah, here we go. The density and the temperature have finally changed on the 206th day. So let's make a note of 206. That's actually the first day out of the year that we're getting any information that's going to be kind of useful to us, if indeed it is. Yeah, and it seems to come in groups. Might depend on which way the satellite's facing. I don't know. I don't know enough about it to know. And then we're getting lots of good data in here. Let's just keep going down. So it's important to inspect your data, especially when it's sort of mystery data like this, and just get a feel for what you might need to do to it. Okay, at the bottom it's all junk again. So that's kind of interesting, or not, as the case may be. So this sort of list data, yeah, the easy way to deal with it is perhaps in a spreadsheet. So let me just copy this. Just copy this entirely into a buffer. You can see that these are all spaces. So the way this data is organized is just with a fixed number of columns. So the year is in the first 4, and then there's a blank, and then we have 3 for the day, and then a blank, and then 2 for the hour, and a blank, and so on. So it's not comma separated data, it's not tab separated data. So we can't do anything with it directly in processing. It doesn't fit the data types that we've dealt with before. So instead, let me come into my spreadsheet. This is LibreOffice, but you can use any spreadsheet you want. And if I just paste in the data, I can then choose what sort of data it is. Tab, comma, separated, semicolon, space. Oh, space. Wow. Okay, let me get rid of these. Space separated data. Huh. Okay. That looks kind of nice. So it's showing me the data here. If I scroll down, it looks like, oh no, this isn't quite right though. Here, these columns have sort of skipped. What if I get rid of detect special number? What if I try fixed width? Fixed width, I can then maybe define like this I don't know, my fields. Let's see. That looks a bit better. Let me see what happens if I hit OK. Ah, yeah, you see, spreadsheets are pretty smart because they deal in columnar data. They know what they're doing. So, yeah, okay. So we have a different piece of data in every column. That's what matters. So if I hit save as and I get this dialog and I choose my data folder, which is under my project, and I'll choose text CSV, comma separated values. But when you hit save, it will actually give some options, so you can have it separated by tabs if you want, and I will. Why not? Tabs are nicer than putting commas through all my data. Even though commas would work, I don't see comma as a data item. So anyway, let's just do it like this with a tab. So save that. Okay. Now we've got this here. Let me give it a name. Maybe I can just call it data.csv. It's open in, okay. This file still has a lock on it. Close that up, try again. There we go, data.csv. Now, if I look at that just as plain text, it looks sort of like this. But you can see this is just one character here because that is actually just a tab in between the fields. So cool, that's not bad. Now, There's something else we can do though to make this even better, and that is we can put in a header line. So we can say year, tab, day, tab, hour, tab, junk, because we don't know what that is, tab, density, tab, temperature. Okay, so what we're doing is we're putting in a header line that explains what the data is, so it's all in one file, and so we don't have to go to this other format file. Let me hit save. This will work very well for us now. So checking out our sketch, all I've done so far is defined a few colors, and I've basically got my setup here. I don't have anything else. What I'll want to do is set up a way of parsing this information. And by now we should be well used to how we do this. The first thing we do is we define a class for our items. So I'll call it a solar item. I'll go through this fairly quickly. We have year, day, and hour as integers, and we have as floats our density and our temperature. So why not just call them the same? So those are the properties. And then when we construct one of these solar items, solar item, we're going to want to pass it all this information. So I'm using my standard formation where I put an underscore after these items because they are sort of temporary variables that come in as arguments. All we're going to do with them is oh, I've got these sort of backwards, don't I? Year, day, hour would make more sense. All we're going to do with these is pass them off to the property. So it's kind of a lot of redundant typing here, but that's the very nature of this. Whoops, density. That's why once you've done this a few times, it's kind of easy, isn't it? Because you're just doing the same thing over and over again. So year equals year underscore, day equals day underscore, and likewise. Right, and that's all we need, I think. That's all we actually need for each item in our table. It's just going to store them like this. We don't really need to do any processing at an item on an item basis. If we do, we can come back and fill this in later. Okay, and now what we need is our aggregate of data that's going to store a list of all of these, or an array list in our case, of course. Again, we've done this many times at this point. It's a design pattern, as it's called, which is fun to repeat because we kind of know it's going to be correct. Oh, what am I going to call this? I'll call it Sol, the name of our sun. New array list of type solar item. Yeah, there we go. And I'm going to give it a place to find the data. I'll call it an URL, even though it's going to be local data in this case. And I'm not sure what else I need at this point, so let's just create our constructor. Pass it an URL. So we can store that in case it needs to. I don't know if it does. It might only need it for the initial stage. And then we're going to parse our data. And as I've shown you before, I prefer to delegate these to another method, just in case at some point we need to parse again at some other place other than our constructor, and then we can just call this method again. This is just a more general solution looking like this. Right, so let's do our parsing. We're going to need temporary variables, much like these. So I'll just use the same names. And we have tabular data, so we can use data of type tab, load our table from our URL, specifying the type. And there's two things we can specify here. First, we have a header line that we can use. The header line means that we'll now be able to address each column by name and not just by number, which is kind of nice. And it's tab separated value. So these two hints tell processing how to read that table. Now I wonder how big that is. It's kind of nice to, I mean, we kind of know how big it is, but in the general sense, it's kind of nice to put out some diagnostic information. So yeah, that's good to start. So in our main program now, we can define our instance that's type solar. How about let's call it Parker? Let's name it after the astronomer. The satellite was named after him, so let's just call it Parker, may as well. And in our setup then we can initialize that as a new solar, and we pass it the data, which was just called data.csv, if I'm remembering correctly. Well, let's see. This should run now. Let's just see what happens. Yes, it did something. And at the bottom, it says 3624. So that's the number of rows of data that we have. So it's nice to know from the get-go that our code is working. I always try to do a test and to run the code ASAP. I mean, we don't know it's all working. We don't know, well, we kind of do. We haven't used solar item yet. Oh, let's do that. Let's fill in a bit more information here so you can have a bit more confidence in what we're doing. I will do the same that I did when we worked with tabular data before, which is that now we have our table. We can use the table row type, and we'll call it our instance of that R. And we can grab the rows one at a time using this method. So this allows us to iterate over the data in an object-oriented fashion. And then within this, we can process R any way we like. And what we're going to want to actually do is just get all our values. And again, we can get them by name. And then once we have all those values, we can create a new solar item with them. So what we want to do is add to our array list an instance. So we're creating a new solar item. Solar item. And to do that, we need to give it the year, the day, the hour, the density, the temperature, like that. This has to match our constructor just below here. Right, so it looks like this is going to work. We don't have any errors showing up, no red lights or even orange ones. But let's pay attention to our data. These values here, we don't want, well, I don't want these values in my data because they're definitely pretty junky. So the density is like 59.9. So maybe it's best to filter these out right away. I'd say so. I'd say it's best to massage your data and get rid of the noise, get rid of the junk right away. So once we have red in our density, we can do a little check. If that value is greater than 99999, I won't worry about the .9 part. Then instead, we'll call it 0. Like so. And then similarly for temperature. So if the temperature is greater than a value, I'll also call that 0, and that value is 1, 2, 3, 4, 5, 8 nines. That's kind of crazy, isn't it? 1, 2, 3, 4, 5, 6, 7, 8. All right, that should work. So this will just, I'm going to put a note in here because this otherwise is kind of incomprehensible code. So treat very large values as 0. I think that's logical to do. There we go. So that should get all our data into our file. Sorry, not into our file, from our file into this class, into a nice array list that now we can manage. But there's a few things we might want to know about this right away. First of all, if I'm going to graph this in some way, it's going to really help to know what the bounds on the data are. I know the smallest value is 0, but what's the largest value going to be? So as well as parsing the data, once it's all parsed, I also want to analyze the data in order to figure out these maximum and minimum values. So I'll set up a stub for this method. So if I'm going to store, well, yeah, I'm going to store the maximum and minimum values. So let me create new arguments for those. I'll just call them dmax and tmax. And then going back down to analyze, I can initialize them first to 0, the lowest possible values they could have that are valid. There are no negative values in this case. I saw that in the data file. If there were, then I'd have to do things slightly differently. Would be no big deal. I think we dealt with negative values before. So let's loop through our data then and just get the maximum values each time through. So for int I equals 0 up to our maximum value. So that is size, and increment each time. And so dmax is going to be the maximum of our existing dmax or our new value. And what is our new value? Whoops, let me just get rid of that error immediately. So that's our data. That's our array list. And we want to retrieve an item from it, which is get, at the ith position. And that will then retrieve the instance of solar item. And the density then is just the property density within that. And something very similar for tmax. It's going to be the maximum of the existing value that we've stored or the new temperature. It's also good to put in some accessor methods so that we can return those values. So for example, we might want to say, what's our maximum temperature? So get max temp, or get temp max in this case. And that will simply return that value. This is good coding practice. And at any time you think you might want a property out of your class instance, you actually create a method to return that. And that way, you've got an interface to your, even though it's a simple return of a property in this case, which we could do, without this. This is just better practice because it means that you can modify this later if you need to. Check for null values or out of bounds data or, whatever else. Right, and that will return the maximum density in a similar way. Now, while we're thinking about it, we probably want a few other things that we might want to return. For example, the size of our data. We just used that here internally. It was sol.size. But what if we want to know that externally? So size of this class is going to be the size of the array list within it. So again, this just means that we can call size on the class instance and it will return the appropriate value. Now we should probably think about how we're going to graph this information, and it's a bit of a mystery to me what the best way might be. And that's why visualization is definitely an exploratory process. You don't really know what data you have. You don't know how good it is or how useful it is. I mean, we still don't know if this data is going to look like anything at all. Maybe it will be disappointing. In which case we maybe need to grab different data sets or look at them in a different way, etc. So I point out that the first chunk of data in this doesn't give us any useful values. It's all zeros. And I pointed out that the day min, let's call it, the first day with useful data was around 206. And likewise, it petered out before the end of the year. So I think we're quite safe to say that the day max is 306. And that is kind of handy because it means we have 100 days worth of data. So let's see our setup. Yeah, we're creating a screen. We're instantiating our data, which does all the parsing right here. And then all we need to do is render our data, which I will do in a separate function for the same reason as always. And so for every item, we need to know its position on the screen, X and Y, and a value. And we'll keep these as floats just for generality, even though we know that positions on screens are actually integers. While we're at it, let's say we want a 20 pixel border around our graph, just so it looks nice. So our X will start at a minimum value of 20 pixels, and our Y will start at a minimum value of 20 pixels. We can change these if we want things to look differently, but it's nice. I like loading up variables with all this so that we don't have a lot of hard-coded numbers in our code. So if X is starting 20 pixels down from the top of the screen, where does it need to end? Like how big is each line going to be? How much do we need to skip? Well, it depends on how much space we have. So we have 800 pixels. So we have, so if I want a certain increment, so I know how far apart each line is going to be, I can start with my height. Let me take off 20 for the border. Might need to take off more actually. And I'm going to divide by the amount of data we have. And the amount of data we have, I said it was 100 lines because what I did was I subtracted 306 and 206. So let's actually have our code do the same thing. Like that. So this will tell us how tall each line has to be. So how tall is each line in pixels? And similarly, we can figure out how far apart each. So how far apart is each X position? That might be able to word that a bit better. So that is going to be how much we're going to increment each X, which is going to depend on our width. So width minus the little border divided by, well, there's 24 hours in a day. We're plotting 24 plots. So something like that. So now this gives us our minimum for each X and Y and how much we're going to increment each by. So now we know all our positions actually of our plot. So let's begin plotting. But I think there's two loops, right? There's each line from the top of the screen to the bottom, and each one of those represents a day. So the first loop will represent our days. And it's going to start with our minimum. And it's going to go until we reach, well, not quite reach our maximum. Or yeah, no, we can reach our maximum. We can make less than equals. And day is going to increment by 1. Yeah, and within that then, we're going to create a shape. And this shape is going to loop through the data for each hour. Well, let's call it H then. And if you remember, the hours were numbered from 0 to 23. So in this case, we want to start at 0 and I has to be less than 24, not less than or equal to. So notice these two loops are slightly different so that they count correctly. And it would help if that was an integer and if I called it H each time. That would surely help. Syntax error here because I don't have semicolons. Fix up my errors. There, they've all gone away. So that's what it's going to look like. So we're going to loop through once for each day, or we're going to loop through each day, and within each day we need to loop through the 24 hours. And that will make one line, so one shape. So this is the skeleton of what we need. So really we need the data per day, because here we need to say, get back our daily data from Parker. Let's just graph the temperatures. Temperature might mean more to me than density. We can work with density later if we wish. So let's get our temperature for that day. And that's going to be a list of 24 items. So we'll put that in an array. Call it temp for temporary and for temperature. Something like that. Yeah. So we need this function. We don't have this yet. We don't have this method. Let's go and write that. So over here, we are going to write a function that returns an array. It's called getTemp. It takes as a parameter the day that we're interested in. Let's set up an array. It's a temporary one, and it is made up of 24 float items, like so. And it would help if I use the right sort of brackets here. So, well, we'll start counting the index at 0, of course, the very first index. We'll loop through our data. So I goes from 0 to the size of our data. And for each data item, we need to check if it's in the day we're asking for. So we don't want all our data returned, all the 3,624 lines. We just want the 24 that correspond to this day. So the first thing we need to do is check that it is in the day. So let's get the data from the ith element. And day is the property of that instance. And if that is equal to the day we have specified, then bingo, we're in luck. We can then put that inside our temporary array at the index point we have, so starting at 0. So let's put that in. And we're getting temperature this time. And then we'll increment our index so that the next time we come to put something in the array, it doesn't overwrite the same position, but does it at the next position. Right, so this will loop through, check that we're on the right day, add that to our temporary array of 24 floats. And then at the end, we just return that. And now that error has gone away because now our definition corresponds to our return value. Temp is not the name of that, it's temperature. Temperature is the name of that. There we go, that's gone away. That's the property here, temperature, that we're returning. So we will do that for the specified day. And now we can just use our temp array. We can do something with this element in temp. But what do we want to do with it? So we have a temperature on a Kelvin scale. We definitely need to scale this though to our screen to get our value. So our value we'll use the very handy dandy map function. So what we're going to do is we're going to map our actual data value. So temp I is our data, but and that goes from 0 to a maximum value that we've defined. Now, I can't remember, did I call it get temp max, the function, the method? I did. Okay, so that's the maximum temperature, 0 is the minimum. So the value we get back this time is going to be somewhere between 0 and our maximum. And instead we want to map it from 0 pixels to probably 20, since that's our y extent. Well, maybe not. Well, let's say it might not correspond to that number, but let's say 20. Let's see what that looks like. So that is our deviation from our y position. So then let's just plot that then. It's at x and it's at y plus v, v being our data value. Yeah, and then I need to make sure I increment my x so that for the next hour, I'm further on in this, on the x-axis building this shape. So I'll increment it by the amount we specified before. Right, maybe I'll write it like this. I'll indent this between begin shape and end shape so it's clear that that is all shape stuff. And then once we have done one line, x needs to be reset to our minimum. Yes, we do need to make sure that each time we start a line, x starts at the beginning that we specified. And we also need to make sure, once we finish a line, that we increment y so we move down the page or down our canvas. Right, this is all quite a lot to take in, but a lot of it is just, you know, managing where our x and y are positioned. Let me just make sure that we have everything we need here. Well, we haven't specified our colors and everything. Yeah, we should do that, yeah. Yeah, let's do it after we do all this initialization there. No fill. Stroke our line in our foreground color that we defined and increase the stroke weight to 2 just so we can see it plainly. Stroke weight 1 is sometimes a bit light. Yeah, what happens if I run this? I get an error. I cannot be resolved to a variable. That's because it's h, it's not I at all. See, I'm always using I for counters. It's h. And y may not have been initialized. Ah, that's true. Y wasn't initialized. So let's initialize y to the minimum value. Any other errors? Let's try it again. There we go. That's very interesting. Now I'm not sure if this actually corresponds to the data. I would have to go and check. But I guess we can see that the data is being plotted here. Quite a lot of the lines are just straight lines. They kind of get in the way. Maybe we could do something about those. Ones that don't have any data, maybe they could be printed lighter, for example. So we'd have to put another check in, though, to see if there's any, if all the values is 0, then before we plot them, we would change our color to something lighter. That might be a nice enhancement. I'm not going to do that now. I'm just going to point these things out. Now I would want to double check that these are in fact our data values. I can't be sure until I go back to our file and sort of compare. So I'd want to go down to the good values here. There were some starting at 206. So 46429 is the value. But that's scaled against our maximum, whatever that might be. Yeah, so there's some stuff to figure out there. So to conclude this tutorial, I would just like to step through our data transduction process and point out which of the 6 steps we did and didn't address in this tutorial. First of all, acquire data. That was certainly part of our process, going to the NASA site and then the Goddard Space Center site and going through their fairly complicated process to obtain the correct data from the correct satellite. Parsing the data, step 2, and filtering out the noise. We certainly had a good look at that in terms of these 999 values that we needed to make a decision about. Also determining which of the data rows was useful to us and which didn't have any useful data. Step 3 is looking for patterns in the data. And that's something which we didn't do extensively. We more or less just used the numbers as they were. The one step that's important there, though, is how we rescaled, transformed the data, which gets into the next steps, really. Step 4 then is choosing an appropriate visual model. And I would debate whether we did that properly or not. I chose a visual model that was very similar to a previous tutorial we did, which I can bring up here. The CP 1919, and in that case, I knew ahead of time that the data had a lot of cultural importance and was sort of graphically bold and interesting in and of itself, even without numbers, even without a way of scientifically interpreting it. It's visually, aesthetically interesting. In this case, I actually didn't know anything about this data or what it would look like. So I went through this project kind of as a counterpoint to the CP 1919 project, in that I'm just blindly looking at data and trying to find interesting things. And I would say that this tutorial in that sense was a failure. I would want to go back to the drawing board to look for better data or something which is more meaningful. I also might need to do more research on the satellite and the sort of data that it's returning so that I can interpret it better. Okay, step 5 is mapping the data to a visual representation. And again, there were signs here that that went wrong somewhere because the quite varied numerical data has been quantized into these kind of plateau in the graph. And that is simply because somewhere I'm using integers when I should be using floats or something like that. So it sort of quantized the data, which actually has kind of an appealing look by accident. And then finally, step 6, interacting with the data for details and so on. I didn't implement that because I wasn't very happy with the visual results, but it's quite easy to see how that might be done. A simple mouse over that would show the actual numeric information for each data point would in fact suffice for a minimal amount of interactivity. So there you go. I thought I would take you through another tutorial similar to those we've done before. Just to show the flip side that not everything works out to something fantastic. This is an iterative process. Once you've gone through the transduction and you reach the conclusions I have, then you can go back. This is an iterative process. Once I've gone through the 5 or 6 steps, I might then determine that I need to go back to the drawing board. Not completely, of course. I now have a body of code. I now have a certain understanding about the data. And so the next time through would be so much faster and easier, and maybe I could find something more interesting in it. So we did look at a couple new things along the way. However, how to use a spreadsheet program to import and export data in column format, but we took it from a column format that was unstructured to a column format that was structured with tabs, and in addition had that header line to help us out. So that was an additional technique which we could use because we're dealing with static data. If we were using dynamic data, then we of course can't go through a manual process like that in the middle. There are ways to automate such things, and indeed one could do a lot more text parsing in Java itself, but in this case, the simplest thing to do was to use a spreadsheet because a spreadsheet's designed for tables, for data in tables. So I hope this has been a useful tutorial. My name's Robin. Thanks for watching. All the best with your projects.